Today is the third lecture in the chemical oceanography module, and we'll be talking about dissolved gases in the ocean. So the other day we looked at the sort of past and how we ended up with the modern ocean, taking a big picture geological view, and I mentioned that we're going to talk about the origin of the atmosphere as well. But before we get there, when we're thinking about dissolved gases in the ocean, we have to talk about the gases in the present day atmosphere. And on the left is a table with the main gases in the atmosphere listed in order of the largest to sort of getting down into smaller ones. And on the right, those same values are presented as two pie charts. And I think it gives you a much better sense of what's really in the atmosphere. So by and large, the main gas in the atmosphere is N2 gas, nitrogen gas. And that's 78% of the atmosphere. 21% of the atmosphere is oxygen as O2 gas. And then there's a small percentage is argon. And then that little red strip in the big pie chart is everything else. And so then if you blow up the everything else and look at what it actually is, you can see CO2 present, carbon dioxide, and then some of the noble gases and all the way down into nitrous oxide, which is another greenhouse gas. And then there's an even smaller little other strip there. So that's what we have now in the atmosphere. And so seawater, the ocean, is in contact with the atmosphere, and seawater itself has many dissolved gases. And these gases exchange between the ocean and the atmosphere. And there's a lot of things that control this exchange. One of them is the concentration gradient, so how much of the gas is in the atmosphere versus how much is in the ocean. Winds play a big role in this. The temperature of the seawater and the salinity of the seawater. So these are all the things that control how much of a given gas that's in the atmosphere dissolves in the seawater. And a key question that's frequently asked in oceanography, and we'll get into this in a bit more detail, is based on the gas concentration in seawater and the gas concentration in the atmosphere, are those gases in equilibrium? And we'll talk about why this matters. So the way we think about gases in the atmosphere is usually by describing them as partial pressures. And so the pressure exerted by an individual gas in a mixture is its partial pressure. So what this means, one way to think about it, is described by Dalton's law of partial pressures. So here where PT, that's the total pressure in the atmosphere, is equal to the pressure of N2 gas, the partial pressure of N2 gas, plus the partial pressure of oxygen gas, plus the plus the partial pressure of argon gas, plus the partial pressure of water vapor, plus all the other gases in the atmosphere. And so nitrogen is 78% of the atmosphere, oxygen's 21% of the atmosphere, and so that's, 78 plus 21, 99% is those two gases. So if you were to ask, what's the total pressure of the atmosphere? You could say, well, the partial pressure of oxygen is here, 159 millimeters of mercury, plus the partial pressure of N2 gas, 593 millimeters of mercury. So the total pressure in the atmosphere is 752 millimeters of mercury. So the sum of everything gives you the total. And on the left, I've given the gas concentrations as mixing ratios, which is mole per mole, so mole of gas per mole of atmosphere, or per mole of air, really. And the reason it's easiest to look at these ways is because they translate to percentages fairly straightforwardly. So at 1 atmosphere of total pressure and 100% relative humidity, the partial pressure of N2 gas is 0.78 atmospheres, which is essentially equal to 0.78 mole per mole. The partial pressure of oxygen is 0.21 atmospheres, which is equal to 0.21 mole per mole. And the partial pressure of CO2 is 0.000402 atmospheres, which is equal to 402 times 10 to the minus 6th mole per mole. And so whenever we're talking about gases and equilibrium and things going between the atmosphere and ocean, we're going to have to do some math, which means we're going to have to pay a bit of attention to units. And so the mixing ratio, which is the concentration of the tables we were just looking at, so this is denoted as C sub X, so this would be for some example gas X. Mixing ratios are given in units of parts per million, parts per billion, or parts per trillion. And so that's what you can see on the left here. where 1 ppm, or part per million, is 1 micromole per mole, or 1 times 10 to the minus 6 mole per mole. And this mixing ratio is also referred to as mole fraction because, like I said, it's really easy to convert these into percentages because it's the mole of gas per mole of air. The reason we talk about gas concentrations like this is that the gas concentration remains constant when density changes. And when we talk about the atmosphere in a couple of weeks, you'll see that the density of the atmosphere changes quite rapidly in the vertical direction. And so it's nice to have a unit that doesn't change. So if we think about normal, everyday interglacial CO2 concentration, so before humans started pumping CO2 in the atmosphere, it's 280 ppm of CO2. And another way to say that is 280 micromoles per mole, or 280 times 10 to the minus 6 mole per mole. Those are all equivalent gas units. And then the other thing we have to think about with the atmosphere is pressure. And so the standard unit of pressure is the Pascal, but we actually don't use this is one case where we don't use the SI unit all the time. We tend to use the units of atmospheres because it simplifies our life. But there's also bars, millibars, hectopascals. There's lots of different pressure units. And you can see on the left here how they're all related to one another. But if we want to talk about mean atmospheric pressure at sea level, the easiest way to refer to it is 1 atmosphere. But 1 atmosphere has been defined as the mean atmospheric pressure at sea level. So if you were to use SI units, you'd use pascals, which is 1.013 to the 5 times 10 to the 5th pascals, or 1,013 hectopascals. And you can see hectopascals are used because they're equivalent to millibars, which is another common unit. You see that a lot in like weather reports and things. You'll see millibars. And then 760 torricelli, which is completely random, but nevertheless a unit of pressure. So the units matter because we're going to be doing some math. And one of the key steps to doing some math, to figuring out gas concentrations, is Henry's law. So when any gas is in contact with water, and so what I'm basically saying is when the atmosphere is sitting on top of the ocean, which it is, some of that gas will dissolve in the water. So some of the gases in the atmosphere are going to dissolve in the water. And this is controlled by Henry's law. So Henry's law is denoted as this capital K with a capital H that's subscripted here. And so Henry's law is independent of any biological or chemical processes in the ocean or atmosphere. So let's just say there's no biology and there's no chemistry, just pure dissolution. Gases will dissolve in seawater in proportion to their partial pressure. And so the way we look at that is for a given gas A, so we'll just make up some pretend gas A, it has a partial pressure of gas A, and then it has a Henry's law constant. And you multiply the Henry's law constant by the partial pressure, and that gives you what you would expect for the seawater concentration of gas A, assuming everything's at equilibrium. So this is the expected equilibrium concentration of the gas in seawater based on its partial pressure in the atmosphere and using the Henry's law. And you can see these brackets here denote concentration. So this is, we use the Henry's law and the partial pressure of the gas to calculate what the expected equilibrium concentration of the seawater is. So I've given you a generic example in the previous slide for gas A, but let's look at it for oxygen, right? So the partial pressure of oxygen times the Henry's law for oxygen. So this Henry's law is gas specific. And you multiply those and it will give you the concentration of O2 in seawater at equilibrium. So we know the partial pressure of oxygen. It's 0.21 mole per mole, which is the same as saying 0.21 atmospheres, or 21% of the atmosphere. And we'll use some sort of a table or some textbook to look up what the Henry's law is for oxygen. So the Henry's law for oxygen at 25 degrees C and a salinity of 35 is this number. And so the units of this number are molarity per atmosphere, so moles per liter per atmosphere. So at this point, with these two pieces of information, we can tell you what the equilibrium concentration in seawater should be. So you take the Henry's law, molarity per atmosphere, times 0.21 atmospheres, and you can cancel these units. So your answer is going to be in molarity. And so you end up with this 0.0022333379 molarity, which is not a very useful number. So we convert it to micromolar, so 10 to the minus 6. So we move the decimal place over 6 times. And the equilibrium concentration of oxygen in seawater at this given temperature and salinity is 223.3 micromolar. So that's how much oxygen should be dissolved in seawater given these conditions, and assuming we're at equilibrium. So this is the sort of example calculation that you guys will have to do in your prac and that I would expect you to do on a test. So there's a clue here in the Henry's law that you have to choose a Henry's law for a particular temperature and salinity. And what that means is that temperature and salinity influence solubility. And if you remember absolutely nothing else from this lecture or even from this course, just remember, please, that cold water holds more gas. Okay? Cold water holds more gas. So what does that mean? So on this plot on the left, we're looking at the solubility of a gas, and this is the Bunsen solubility, but essentially you can just think of it as a general solubility term. So higher solubility means more of the gas gets dissolved. And if you look on the x-axis, we have temperature. So as you move towards the left, meaning as the water gets colder, you can see the solubilities all get higher. These lines slope up for every single one of these gases. So as the water's colder, it's capable of holding more gas. So there's a higher solubility. And the plot on the right is the exact same data, but now just zoomed in on, you can see it's lower in the scale because krypton and xenon are so much higher than the other gases. But it holds true for all these gases, argon, oxygen, N2. As you go to lower temperatures and it gets colder, the solubility is higher because that colder water is capable of holding more gas. The other thing that matters is salinity. And this is the other key here. Fresh water holds more gas. So actually, before I go on, let me explain a little bit about why this is. Okay, so when the molecules in something warm are moving faster, right? They're bouncing around all over the place. And it doesn't leave a lot of space for any gas to come in and dissolve. As you slow these water down, the molecules start to move a little bit slower, right? And there's more space for gas molecules to come in and dissolve themselves in there, as opposed to when here, they're going to just keep bumping into the water molecules and they're not actually going to be able to dissolve. So that's another way to sort of think about why cold water holds more gas. And so the same rationale sort of applies to salinity and solubility. So if you have a bucket of molecules of fresh water, let's say, and then you have a bucket of molecules of seawater, there's all the salts in between all the water molecules, right? And so there just isn't as much physical space for the gas to go in as there is here in your fresh water, where there's lots of room for it to fit. And so you can see this on the right-hand plot. It's again the Bunsen solubility on the y-axis and temperature on the x-axis, but now we've got two lines for each of the elements. Fresh water is the solid line, and then salinity is the dashed line. And so you can see that for any given temperature, the solubility is lower when there's salts present. Okay, and that's again because there isn't room. There's this interference of ionic strength because of the solute-solvent interactions. And so these solubility lines are depressed when you have higher salinity. So if we look at the Henry's law constant for O2, for oxygen gas at 25 degrees C and a salinity of 35, this is the number we used in the previous calculation. You can see now to make the number more manageable, I've changed it to micromolar per atmosphere. So it's 1063. And if we lower the temperature, so colder water with the same salinity, you can see now has a higher solubility. So more gas will be able to be held in this parcel at 0 degrees C and 35 PSU. And then if we take the salts out and we make it fresher, all right, so now this is comparing to the first one. So 25 degrees C versus 25 degrees C. But now instead of a salinity of 35, we have a salinity of 0. You can see that the solubility is higher. So 1300 is greater than 1063. So here, moving on to how we calculate gas concentrations, and I'm going to do some examples at the end of the lecture here. This is a view of what the actual measured gas concentrations are in the ocean. So this is annual average oxygen, and the units here are milliliters per liter. One of the annoying things about talking about gases in the ocean is that there's a million different units that people use, and it can get a little bit confusing sometimes. I'll try to keep it straightforward for you guys. But you can see that there's quite a bit of spatial variability in surface ocean oxygen concentrations, and this is the scale on the color bar scale. So in general, we've got lower surface ocean oxygen concentrations in the low latitudes and then increasing to the high latitudes. So based on what I just told you, salinity in the surface ocean varies a little bit, but not a ton. But surface ocean temperatures definitely vary quite a bit. And so what you're seeing here is the temperature effect. So these cold waters in the higher latitudes are capable of holding more gas. And so the atmospheric concentration of oxygen doesn't really vary, right? It's pretty much always the same, 0.21 atmospheres. But this colder water is able to hold a lot more of that gas. And so you end up with much higher concentrations where the waters are colder than you do in the subtropics and tropics. Okay, so Henry's law allows you to calculate what the equilibrium concentration in the ocean should be, but that isn't necessarily what you find when you go out and measure gases in the ocean. And so when you go out and make a measurement, we refer to this as the in situ concentration. And you can compare the measured concentration to what you would expect for your equilibrium concentration. And this is very useful because you can describe then the seawater as being supersaturated, undersaturated, or saturated. So when you go out and make a measurement of gas A in seawater, and it's greater than what you calculated as its equilibrium concentration, you can say that water is supersaturated with that gas. There's more of that gas in the seawater than we expect. If you go out and measure the concentration of gas A in seawater, and it's less than you calculated for the equilibrium concentration, we can say that gas is undersaturated. Something in the seawater is removing that gas, and you're not able to establish the equilibrium. Sometimes you go out and make a measurement, and it's exactly what the equilibrium is, which is you would say that it's saturated. But we can calculate this degree of saturation, and we refer to this as the percent saturation. So you take the measured gas here, divided by your calculated equilibrium and multiply by 100, and that tells you your percent saturation. And what we do in order to, so you might know that, you might be able to find the Henry's law everywhere, but thankfully somebody has gone through and calculated the equilibrium concentrations, especially for things like oxygen. It's really easy because the concentration of oxygen in the atmosphere is constant. And so if you just have a table of all the Henry's law values, all those KH numbers at various temperatures and salinity, then you can make these tables, which are your expected equilibrium concentrations. So this makes it super easy, right? So you find the temperature of your water here, and then you find the salinity of your water here, and then you look. So you say, my water is 10 degrees C, and the salinity is 34. So the equilibrium concentration of oxygen is 273.3. In this case, the units are micromole per kilogram, and you can compare what you go out and measure to this number from the table. So if you measure this exact number, then it means your system's at equilibrium. And that doesn't mean there's no gas exchanging, but it means the rate of ingassing to the ocean and outgassing are equal. And this, of course, this equilibrium value is a function of temperature, salinity, and the partial pressure of the gas in the atmosphere. So I've explained that sometimes you have a supersaturation and sometimes an undersaturation and sometimes you're at equilibrium, but why would you not be at equilibrium? We haven't really talked about that at all. And there's two main things that would lead to deviations from equilibrium. The first is physical effects, so things like wind, and the other would be chemical effects. So something's happening to the gas in the ocean that's changing equilibrium. Not all gases are influenced by both physical and chemical effects. But some gases definitely are. All gases are influenced by the physical effects because you can't escape wind no matter what. But not all gases, have chemistry that happens. So the gases that are only influenced by physics are useful. They're called the non-reactive gases, and they help you isolate and identify what the physical processes are, so temperature, salinity, wind, etc. Some gases are reactive, such as oxygen and carbon dioxide. And so they're, of course, influenced by the physics, but they're also influenced by biological and chemical processes. So what this means, I'm just going to go back for a second. So oxygen is influenced by temperature, but as I've said, it's also influenced by biological and chemical processes, right? So in surface oxygen, places where you have a lot of photosynthesis and a lot of productivity are going to release oxygen. And so even though it looks like, you look at these, you can't actually know just by looking at these values in the surface ocean if you're at equilibrium or if there's been some gas added to the surface ocean, some oxygen added because of photosynthesis. You actually have to take each one of these values and compare them to your equilibrium concentration to know if you've had some oxygen added due to photosynthesis or removed due to respiration. Okay. So where was I? Here we go. So I just wanted to do a little example calculation to show you guys how this works. So if you go to deep water in the eastern basin of the Atlantic Ocean, a typical oxygen concentration that you would see is 239 micromole per kilogram of seawater. And so the salinity of this water is 36 salinity units and the temperature is 1 degree C. And so the question is, what is the percent oxygen saturation of this water? So is this water at equilibrium? Is this the concentration you'd expect? So the first thing you have to do is say, all right, well, what's the equilibrium concentration? So on the right-hand side, we have one of these tables that gives you the equilibrium concentration. Okay, so 1 degree C is between 0 and 2, and 36 salinity units is here. So it's going to be something between these two values. Did I get that right? Yeah, okay. So you could essentially take the average of these two values because the average of 0 and 2 is 1. So you'd say 328.3 plus 345.8 divided by 2 to get the average value, which is roughly 334.5. And you can see the tables also in micromole per kilogram. Micromole per kilogram. Okay, so your measured value is definitely less than the equilibrium value. So you are not at equilibrium. You are definitely what we would call undersaturated. Okay? Undersaturated. So, and the equation to determine the percent saturation is your in situ, your measured value, which is 239, divided by your equilibrium value, which we got from the table, which is 334.5, times 100. And what that gives you is, if I'm doing this correctly, 71.4%. So this parcel of water is undersaturated, and its percent oxygen saturation is 71.4%. Okay? And so based on what we know about photosynthesis and respiration, this makes sense because this is deep water, okay? So photosynthesis happens at the surface and respiration happens in the deep. And so respiration consumes oxygen. So we would assume, and we would propose, that the reason this deep water is lower in concentration than you'd expect from equilibrium is that the oxygen in this water has been consumed because of respiration. And that indeed makes sense. And so you can then use this number, this percent undersaturation, to have an idea of how much respiration has probably happened. So that's just sort of an example of how we would use these percent saturations. Okay, another example. So in the previous example, we used a measured an equilibrium value to determine percent saturation. In this case, we're going to actually determine what the equilibrium value is. So the partial pressure of CO2 in the atmosphere today is roughly 403.4 ppm. It's probably a little bit higher now. So what is the equilibrium seawater concentration of CO2 for a water mass that has these properties, so 0 degrees C and 35 salinity? And it asks to give the concentration that you calculate in a couple of different units. So in order to get the equilibrium concentration, you need the partial pressure, which you have, and you need the KH value. And so here you're given the KH value. The Henry's law for CO2 at this temperature and salinity is 0.06582 moles of CO2 per kilogram seawater atmospheres. Okay, so first issue you have is that your partial pressure is given in ppm, and your Henry's law uses gas concentrations in atmospheres. So you need to go back to that slide where I showed you how to interconvert between different units. And doing that, you would see that this partial pressure is actually equal to 403.38 times 10 to the minus 6 atmospheres. Okay? So if you multiply 0.06582 moles per kilogram atmospheres times 403.38 times 10 to the minus 6 atmospheres. You can cancel the atmospheres, so your answer is going to be in moles per kilogram. Okay? And so in this case, you end up with a value of 26.55, and I'm going to give you in micromoles because it's too big otherwise, micromole per kilogram seawater. So that's your equilibrium concentration of CO2 in this gas parcel in units of micromole per kilogram seawater, which is here. So I've also asked you to give it in micromoles per liter seawater. And so to go from micromoles per kilogram seawater to micromoles per liter of seawater, you need to know the density of seawater. And so you would then go to a density table. So here I've got a density table. So of course you'd need to be given a density table. So it's 0 degrees C and 35 PSU, which means it's this value here, 1028.107, and your units are kilograms per meter cubed. So I'll go ahead and write that here. So 1028.107 kilograms per meter cubed. So that's helpful, but you actually want it in micromoles per liter, not meters cubed. So what you actually have to do here, the way you have to set this up, and I'll do it down here at the bottom. Okay, so you've got your gas concentration here in micromoles per kilogram. And you need to multiply that by your density, which is 1028.107 kilograms per meter cubed. So your kilograms here cancel, but you actually need to look up at this point is that you have volume in meters cubed, but you want volume in liters. And so you would just need to Google that conversion, which is 0.001 meters cubed is 1 liter. And so now you can cross off meters cubed. And what's left now is micromole per liter. So you would do 26.55 times 1028.107 times 0.001. And that gives you 27.3 micromoles of CO2 per liter of seawater in this case. Okay, so this problem is a bit more complicated because you had to convert the units of your partial pressure. And then once you got your answer, you had to convert to a different type of units using density, where the density, you had to convert the units a little bit. So you can see there's more to this question than just understanding how to calculate an equilibrium concentration. You have to keep track of your units and make sure you end up in the right place. So that's it for the dissolved gas lecture, and you guys will get to do some homework problems like this on the practical, and like I said, you'll definitely be expected to do stuff like this for the test, and I encourage you to go to your tutorial sessions